Thank you, Lapo. First, I wanted to thank Barbara for organizing this workshop. It's been the second year, and I think it's fantastic to have that kind of workshop 2 years in a row here in Paris. And I wanted to thank her also for inviting me. Mantle convection and plate tectonics provide a central framework in solid earth sciences. Tectonics is the surface expression of convection within the mantle. In practice, though, convection models have pretty much failed to reproduce surface tectonics that is like the Earth. But ultimately, the theory of mantle convection has the potential to unfold jointly surface tectonics and convection in the interior together. So I would hope to convince you today with this talk that we are kind of on the way to make this dream come true. So the work I am presenting aims at linking surface tectonics with mantle convection. The goal is to give us a new sort of imaging of the mantle, which will be independent of seismology, and to provide means to realize a new type of tectonic reconstruction, which is not made only from not made from plate tectonics. So it is a team effort, and I want to acknowledge my students and colleagues for this work. Tectonics and geodynamics get along well together. They are good buddies because they both speak the same kind of language. They speak about kinematics, about temperature changes and pressure changes. However, it's kind of an awkward relationship because tectonics deal only with, let's say, the two first 100 kilometers of the mantle. And convection models, they have really a hard time to predict tectonic observations. So they have all the means to be very good buddies, but still they have to work it out to be normal buddies. The main problem with convection models is to account for shear localization. So at the surface of the Earth, strain is often restricted to very small volumes. Sometimes shear zones like this are restricted to 1 to 10 kilometer width, and you have all the strain of the region within this kind of very limited area. So in such regions, strain is very intense, and it looks like a flow of soft material at the lithospheric scale. Along with this issue, convection models have difficulties to generate toroidal motion. Transform fault is a case of pure toroidal motion, localized toroidal motion at the surface of the Earth. This motion is very peculiar because it plays no role in transporting heat vertically, so it does not cool the system. However, we estimate that this toroidal motion is about 30–40% of the whole motion of the convective flow. So to try to deal with these issues, in fact, we built sort of ad hoc, there will be progress, but yet we built rheologies that localize shear and produce some toroidal motion. This kind of rheology is called pseudoplastic rheology, and we kind of specify the yield stress at which the viscosity drops down. It's a sort of strain rate softening in a way. So with such rheologies, if we want to reproduce the motion at the surface of the Earth, tectonics of the Earth, finally, we need a resolution of 1 kilometer. So this is why I put this kid with a magnifying glass, because we need to look to, we have a big system, and we need a resolution of 1 kilometer. So the group of McGurnis, with this paper of Stadler and co-workers, have resolved this resolution, and they predict a surface tectonic with such rheologies that is kind of similar to the Earth, with a lot of input, of course, but it's the best we can do. But if you do that, you can do it for one time step, but you cannot do it for millions of years of integration in convection models. It's not possible yet. It's too difficult for the computers. So what we can do is to smooth this rheology. It's not as good as we want. We won't have shear localization on 1 kilometer shear zones. It's going to be much wider. But we still produce shear localization, and we can produce toroidal motion and a sort of plate-like behavior. Paul Tackley from Zurich has been pioneering these models for several years now, incorporating this kind of rheologies within global mantle convection models. And all the following results you will see are obtained with the approach he built over the years. So here, it's a snapshot of a model we made to show you that with this kind of rheology and imposing continents at the surface of this convection model, continents that can move, we have a seafloor spreading that is quite like, that has some, at a first order level, some Earth-like characters. So what you can see here are, so it's a map of the edges of the seafloor produced by a convection model that is on the right side. You see here ridges, you see here triple junctions. What you can see also is in some locations is subduction of young seafloor, which you don't see in classical convection models. So you have first order characters that look like the seafloor spreading of the Earth. You also have continental drift, which is quite like we expect from the Earth, although we don't have so much information about it. But what you see here are convection models over which you have continents here, 2 continents. So where it's red, it's very stiff continents. When it's blue, it's softer continents, softer parts of the continents. And you have an evolution. And you have here a dispersal of these 2 continents, and after some time, aggregation of these 2 continents, and the same kind of thing here. So looking at the time scale, there is sort of statistical cyclicity of dispersal and aggregation, which is a bit like we expect from Wilson cycles. So we have models that produce seafloor spreading and continental drift at a first order level that are quite like the Earth. Of course, I'm excited about this because it's very, for me, it's very innovative models because we can make tectonics on these models. These are models that you can make tectonic predictions out of. I will give you an example here. So this is a situation where you have 6 continents of the same size. They are simplified continents, of course. And you have, in this situation, 3 oceans, one here, let's say one here, and one big here. So you have a big rich system here, one here, another one here. So we start from this situation. It's dominated here by older seafloor, I would say. So the production of new seafloor here is 3.3 kilometers per year, square kilometers per year. Several tens of millions years after that, the production increases in this model. This ocean is a bit changing. Maybe you've seen the continents drifting a little bit. And after a little more time, you have a new ridge system coming here, and you have a new configuration in the seafloor spreading. You have almost doubled the production of new seafloor at this time. And after some time, you get to a new situation where continents have drifted, new oceans. What I wanted to show you here is that if you want to, you can do a sort of virtual tectonics on this, with these models. And you can estimate how on the Earth, over a billion-year time scale, the seafloor spreading can vary. And here, we've seen that variations of the seafloor production rate by a factor of 2 is something we can expect in these models, and maybe for Earth-like seafloor spreading. So the great thing is that we can make prediction out of it. We can make predictions. Can we make even, even more interesting predictions for us? So the question I'm going to try to answer is: can we use observations of tectonics together with mantle convection models to predict past tectonics and convection evolution together. Okay? Can we do like in meteorology? Can we use data we have, models that make predictions that are fair? They're not perfect, but they're already quite good. Can we use them jointly to unfold the past tectonics and mantle flow together? So it's not so easy. It's not so easy because our models are not perfect. The observations have errors. So we have uncertainties. And mantle convection, as you may know, is a chaotic system. And when you have a chaotic system, the uncertainties you have in the initial conditions, for instance, they're going to grow. And you're going to diverge from the solution you're looking for. So it's called the butterfly effect. You may know that. If I state this for mantle convection, a tiny plume in the Arctic can cause a subduction in the Pacific many years after. So this is a real problem, and it is very important for us if we want to do predictions, data assimilation, to know what is the time scale over which we can do data assimilation. And we don't know it yet. So we need to compute this time of predictability. For the weather forecast, for instance, for the atmosphere, this time of predictability is about 15 days. It means that after 15 days, you won't be able anyways to predict the weather because of the intrinsic chaotic nature of the system. So what is it for mantle convection? It's part of the PhD thesis of Léa Bello. A classic way to evaluate the time of predictability is to realize what we call twin experiments. It's been proposed by Lawrence in the 60s. So what we do is that we compute a reference convection solution over a long time scale. And we compute a kind of twin, which is exactly the same solution, but that we perturbed initially with a little errors. It represents the uncertainty we could have on the initial state. It needs to be tiny errors because if we want to use the theory of Lorentz, we need to have errors that we need to. It's a linear theory, so we need to start with tiny errors. So what is very common in the study of chaotic system is that we evaluate the growth of this error as a function of the initial error, and this growth is exponential. And a function of this lambda here that are Lyapunov exponents. I don't know if you know that. The inverse of the Lyapunov exponent is what we call the e-folding time or the Lyapunov time, which gives a time scale over which an initial error will grow by a certain factor. So here we realized a twin experiment for a convection model over which we put Earth-like continents. So it's not the Earth, it's a virtual Earth. We put continents like on Earth. What you have here is the viscosity of the system in colors. The blue continents are very stiff, so very viscous. What is green are quite stiff oceans. And red is where the stresses are very important, and we reach the yield stress, so we have softening and creation of shear zones. So in a way, these zones are sort of plate boundaries, analog to plate boundaries. This is the reference solution, and this is the reference in which we have put a very tiny error randomly everywhere in the system. So I show you how the system will diverge, although sorry about that. Although the initial error is less than 1%. So when you start, you have the same kind of tectonic system with this big here. What is it? I think it's a subduction system. Convection, continents, they move a bit the same in both models. What you can see already here is that there are differences in the tectonics in these oceans, and even more right here. So at some point, even though the continents have a kind of similar motion, you don't recognize the tectonics from one model to the other. You know, it becomes to diverge quite drastically. So the time of integration here, I think it's something like 500 million years. So you see here, you have a triple junction here. You have one here, but it's not the same. It's really somewhere else. And right there, in this ocean, it's very different. Right. So here it's the end, and you have a heart-shaped oceanic plate. Anyways, what I wanted to show you here is that the introduction of tiny errors caused the growth of errors. What it means for, if you want to go back, even if you may have heard about transporting present-day heterogeneity backwards in time to infer past mental structure. When we do that, we do that over 30 million years because we are afraid of thermal diffusion, because we need to do that before thermal diffusion play any role. But you have also this effect of chaotic growth of error over the 30 million years of backward integration that can play a role as well. So these errors, how do they grow? We have I show you two kinds of models here. This plot is for isoviscous models. The viscosity is everywhere the same. At the surface, it's not like plate tectonics. And these are plate-like models with the rheology I talked to you about. So with isoviscous model, the error grows exponentially. So it's a log plot, exponentially, until it reaches a plateau. Here, it's the maximum error you get. It's about 10%, so it's about an error distributed everywhere of between 2 and 300 degrees. The error growth, as predicted, is not dependent really on the initial error, and the e-folding time, the Lyapunov time here, is about 30 million years. When you do the same kind of thing, experiments with plate-like behavior, the error growth is not exactly the same. You know, it's more like time dependent, but we can still have a correct, a fit of this error growth, and it's about here the Lyapunov time, the e-folding time, is about 190 million years. So when you have plate-like behavior, you have longer wavelengths, more stable. Although the convection is still chaotic, and you, in a way, you have more time to propagate your error, and it's easier to make predictions with this kind of system. So we can estimate that we can make predictions over a certain number of e-folding time with data assimilation, depending on the error we have on the data we will use. So this time frame gives an idea over which this time we can reconstruct jointly tectonics and convection together. So I'll show you now very preliminary results, which are the work which make the work of PhD work of Marie Baucher. Her work is dedicated to make sequential data assimilation, and sequential data assimilation is a bit like mastermind. You incrementally improve your reconstruction by adding information in your system over time. I want to use the sequential data assimilation as a proof of concept to show you that we can reconstruct really from tectonic data the tectonics and the mantle convection together. I need to explain you what we will do in a more formal way. So we want to predict mantle structure and tectonics together. We start from an initial state, and what we have in initial state is the green one. So the first guess we have on the system. At this time, we have also information on this system. It's partial information. Since we use tectonics, it's surface information. Using statistics, over the model, and this information and the error we have on these informations, we can correct the initial state to a new one, which is going to be the best match between the observations we have and the physics we know. From this, we can start a convection calculation, over which we make predictions of tectonics and convection. And we reach a new state. At this time, we also have information, observations, and we do the same like here. We make this correction, which is called innovation in data assimilation. So we will use this information, the information we have on the physics of convection, and we correct it. And again, we run the convection models until a new time at which we have observations. And we go that repeatedly, sequentially. And as time goes on and observations are assimilated, we improve the prediction we make on the tectonics and the convection interior. So this is the way they work usually for weather forecast. The technique we use is a sort of Kalman filter, a simplified one. I just wanted to give you some glimpse of how it works. What we do is that we make statistics of our convection model. So we run a very long experiment of convection. I mean, we compute a very long solution of convection. And we try to see how the velocity, the heat flow at the surface is correlated to the temperature everywhere within the calculation. So it's what I show you here are sort of sensitivity, what would be sensitivity kernels for seismology a little bit. Here it's the correlation between a sort of perturbation we would make of the heat flow at the surface. The correlation between this perturbation and the temperature everywhere. So you see that when you have some information of the heat flow at the surface, knowing how the convection, the physics of convection, you can probably make corrections mostly in the boundary layers where you have very positive or very negative correlation. But it's difficult to reconstruct really what's beneath the boundary layer. But this is kind of already known. When you have information of the surface velocities at the surface, you have a probe of the interior. So it's not very deep probe, but still, it's a way to have information of the interior. So we know the correlation between the velocity, the heat flow at the surface, and what goes within the system. So we have all these correlations, these cross correlations, things like that. So it's a lot of information on the physical system. So we can use this statistical information together with the observation at the surface to guess how we need to correct the convection state to make it the best fit between the physics and the observations. So it's a first try. It's not perfect. But this is the first guess of our model. We have no information a priori. So the way we built this convection first state, this is for a virtual case. I here try to see if the method can work. So this is the average, at each point, the average temperature of the system. Okay. In the statistics, what I was talking about before, the correlations are linked to the standard deviations. Here, the first guess is only the average of the temperature at each point. What I want to find is this true state. In a way, it's virtual today. And I will try to do that over an integration of sequential data assimilation of 100 million years. So here, I show you the reconstruction we make. We want to have that, but we have this. But here, we have two steps of assimilation. We have data, observations at the surface of heat flow and surface velocity at 100 million years, and today, in this virtual case. And we already, from this, we already make predictions of subductions, downwellings that are not so bad. We reconstruct the boundary layer not so badly as well. If we increase the number of steps of assimilation, here we We make corrections every 20 million years with the method I talked to you about. And we have a much better reconstruction of the interior of the system. So what I show you here is that from the tectonic data we have at the surface and the heat flow information, we can reconstruct the interior of the system. We can make some sort of imagery of the interior of the Earth from tectonics, a bit like seismology does imaging of the interior from the seismic measurements of the ground motion. Okay, I think it's a way we have an imaging which could be independent of seismology. So we still need to improve. We need to get more strength. The models I showed you are quite simple. The rheology, we need to improve on the rheology. We need to improve on the resolution. We need to improve on many, many things. So it will take some time to get to where we want to. But we also need to improve our data assimilation strategies. This was a kind of a simple one for a proof of concept, but we can use data assimilation strategies also to reconstruct tectonics. At times we have no information in the oceans, for instance. So I'm kind of excited because I just got a ERC grant about this to develop these data assimilation strategies. I just make some advertising here because I'm going to be looking for postdocs or PhDs, so if anyone is interested, you can contact me. The ultimate goal is really to reconstruct the tectonics. At times we have no information. At times plate tectonics cannot work, but mantle convection has the potential to work using data assimilation. Thank you.